Let's understand the next concept, that is symmetrical short circuit of synchronous generator under no load constant excitation. So about this concept of synchronous generator, the working principle, and what all happens when we are loading the generators, and the importance of variable excitation and constant excitation, all those things we already discussed in the previous semester. So it is a high time to refresh the concepts. So here just we are will discuss that the working principle of the synchronous generator, and what is the function of stator and the rotor, that is nothing but the field and armature. Then the important concept of damper winding. Okay, let's see. We'll understand that what are all the things we need to remember while discussing these concepts. When the current flowing through the armature of the synchronous generators, the terminals are suddenly become short circuited. This is similar to that the current which is flowing through the RL circuit, already we discussed in the previous slides. So keeping in mind that the supplied, which is the formation of sinusoidal source. However, there is an importance difference between than in the case of RL circuit and to the synchronous generator. That is, we have something uh, the reactance, that is nothing but XL value, that is omega L, which is a constant quantity, whereas in case of the generator, the reactance is not constant, but it is a time of, but it is a function with the time. So before we understanding that how does the reactance which is going to vary, we'll verify briefly in touch up with the sub concept of working principle of synchronous generator. So we know that synchronous generator, which is a consisting of armature winding, which are symmetrical for the three phases on the stator, and there is an field winding which is wound on the rotor. Also in the field structure, which are placed with the damper windings, so which you can see here. Okay, these are the damper windings on themselves at the both ends. So the field winding which is excited by, which you can see, which is excited by DC current. So whenever there is an rotor which is going to rotate with the acting by the prime mover, the armature winding, this is the armature winding, is cut by the magnetic flux on the field winding. Okay, hence there is an the three phase alternating EMF which is going to induce in the armature winding. Okay, in turn, so resulting in that there is an three phase current which are set up in these windings. So this is going to produce the rotating magnetic field which is going to rotate at the synchronous speed in the air gap between the stator and the rotor. So when this field structure are rotating at, these are the field structure which are rotating at along with an rotating magnetic field produced by the armature winding. So during normal operating condition, so what will happens, the field which is produced by the armature current will be relatively stationary with respect to the field winding and the damper winding, these two, field winding and damper winding. So resulting in the magnetic field will not induce any voltages and the current in the field and the damper windings. So during normal, this is what happens during the normal operating conditions. So resulting in the effective reactance of the armature winding is not being influenced by the field and this field and damper windings. So this you can see here. Okay, so these are the damper windings with the end pole which are faced. Okay, so these are going to help. Already we know the concept. Okay, then so under steady state condition, this armature reaction of the synchronous generator, which are going to produce, there is an demagnetizing flux. So this causes there is a drop in the machine, and this is nothing but we are going to assuming a fictitious reactance. That's nothing but we can call it as the armature reactance. So the reactance due to the flux set by the armature winding, but not which is going to cross the air gap. That's nothing but we can call it as it is a leakage reactance. This is denoted by XL value. So by adding up these leakage reactance and the armature reactance, we can call it as the XA, that is nothing but the synchronous, which is denoted by XS, okay, or this is X is equal to XS, adding up for these two. So that is nothing but we can call it as synchronous reactance. So neglecting the armature reactant, armature resistance, the steady state model of the synchronous generator on single phase basis, which was denoted by this equation. So that is X is equal to XL plus XA, armature reactance and the leakage reactance. So when there is an alternator suddenly undergoes, if there is a short circuit, so what will happens during this condition is armature current, which is going to change from a low value to the very high value in all the three phases because of this short circuit. So we know that in the case of transmission line, which is discussed in the previous concept, okay, the armature current will have an AC component as well as DC offset current. So this will be different in each phases and is accounted for separately on empirical basis. So this usually the multiplication factor will be around 1.6. This the figure which shows that the trace of the armature current when neglecting the DC offset current will be shown in this figure. So this current will be similar in all the three phases except for a phase angle difference between 120° with the electrical. So this is what we can see. So if there is a fault, suddenly there is an transient current. After subject to some time, okay, this is going to sustain. Then there is an initially this is transient, then there is a transient. So we can able to attain a steady state. So that we'll understand how actually this transient and the steady state condition will take places. So already I told that if there is an occurrence of the short circuit, so what will happens? So there is a rotating magnetic field which was produced by the armature. This is going to changes in a magnitude with respect to the damper windings and with the field windings. So hence there will be an induced EMF and the current in the filled and the damper windings. So the induced current in these two will be such a direction which is going to opposite to the magnetic flux which is produced by the armature conductor. It's armature. So resulting in there is an equivalent reactance to the armature which is reduced. So this reduced reactance we can call it as subtransient reactance. So that is denoted by X double dash. So this can be represented by two reactants which is in parallel, okay, which you can see here. So XA is parallel with XL and XD, and in series with XL is nothing but leakage reactance. So X double dash can be written as XL plus 1 over 1 by XA plus 1 by XF plus 1 over, sorry, that is 1 divided by X dW. Okay, so these are nothing but XF is the field winding reactance, and XdW is nothing but the damper winding reactances. So here this is nothing but we can denote it as subtransient reactances. So you have to see here O, A, B and the C value. A is subjected to the steady state, B is subjected to transient, and C is subjected to that subtransient periods. Okay, so it is a composition with DC offset and the symmetrical components of the current. So this is X double dash which is explaining that. So here the induced current in both field and the damper windings which is going to decay exponentially, which is depending upon their time constant, that is tau is nothing but value, okay, and the decaying component mainly is depending upon the that is a constant value, that is L by R ratio. Okay, so the time constant, this is the time constant damper winding which is less than that of the time constant of the field winding. So hence the induced current in the damper winding which is going to dice out very fast within a few cycles. So hence XdW become an open circuited and resulting in there is an reactance. Okay, so that is nothing but X dash which we can, okay, X dash which we can denote it as transient reactance. Okay, so whenever we are writing that X dash, that is transient reactance. Okay, so resulting in this is a circuit. So XA, because XdW which is short circuit means which is very less, so hence this is open circuit. XA which is parallel with the field winding and the reactance means the leakage reactance. So X dash will become XL plus 1 by XA plus 1 by XF. Okay, so this induced current in the field winding current will also, which is going to die out in a short time, which is depending upon the time constant of the field winding. So this effect is which is equivalent to open circuit of XF, the field winding, and thus the armature which is going to regain its normal reactances, so subjected to the X value. So we'll understand that what do you mean by subtransient, transient and the steady state. So subtransient period which is going to usually lasting only for first two cycles, so at which the current decrement is very rapid. Okay, then if it is subjected to transient period which is going to cover relatively longer time, usually 5 to 8 cycle, so during which the current decrement is somewhat moderate. and finally we will get a steady state period. So from the waveform, so we have to calculate the current of I dash and I double dash. So I is nothing but RMS value of steady state current. I dash is nothing but the value of during DC offset component. I double dash is nothing but subtransient current, which is excluding the DC offset component. So already we know that from the waveform, I is equal to Y is for subjected to steady state. It is a by root 2. I dash, okay, subjected to transient, and this is subjected to subtransient value of the DC offset current. So from this, there is a gradual decrease in the current is because of the time varying reactance. So already that's we know that it is depending upon the two value, that is L by R ratio. So hence we can conclude that so reactance, okay, E by that's not Eg by I double dash, that's nothing but subtransient reactance is equal to EMF divided by subtransient current. So already we know that I double dash is nothing but OC by root 2. Similarly, transient reactance is equal to Eg by I dash. So we'll get Eg by OB by root 2. So similarly for the reactance, that's nothing but steady state, we'll get Eg by I, that is Eg by OA root 2. So this is what, based on these expressions of the various currents and the reactance should under during short circuit. So these values are very useful to selecting the protected devices under subjected to that steady state, transient and the subtransient value of the reactances. So you will understand that uh, so how important it is, all those things that we understand in power system protection subject. Let's understand the next concept is short circuit of a loaded synchronous generator. So in practice, before the short circuit, generally the generator would be mostly on load condition. So this determination of the short circuit currents when the machine is on load, which is involves the determination of the internal voltages considering subtransient, transient and steady state reactances. So these are the voltages which are obtained by adding vectorially the subtransient, the transient and steady state reactance voltage drop respectively due to the load current, that is CPD upon the load value, to the terminal voltage V. Hence, so this can be written as Eg double dash, okay, that is equal to V, the terminal voltage, plus the load current and the reactance of the subtransient and the transient V plus IL, okay, JIL into the transient reactance, and this is the steady state. Okay, Eg is equal to V plus J into IL value into XD. Okay. So these circuit model of the synchronous generator which are shown here. So that is nothing but if it is subjected to that the different condition, subtransient, transient and steady state, okay, the EMF will be subtransient EMF and the reactance resulting in the load current, and this is for the transient EMF, reactance, and the load current. Similarly for the steady state EG, XD, and the IL value. So these synchronous motors will have the internal EMF and the reactance which are similar to that of the generators, except that the current direction which is reversed. Okay, in place that the generator which is going to deliver, the motor which is going to taking that the current from the source. Okay, so this is which is shown here. Okay, em double dash is equal to v minus j il into x d double dash. Okay, subtransient and transient em dash is equal to v minus jil into x d dash. Similarly, that is em is equal to v minus j il xd. This is what there is a small difference between the generator and the synchronous motor. Next concept is analysis of three-phase symmetrical fault. The symmetrical fault can be analyzed with the help of the single phase basis using the reactance diagram. The fault analysis, which has to be performed separately for the subtransient, transient, and the steady state condition of the fault, because we know that the reactance and the internal EMF of the synchronous machine will be different in each state. So once the per unit reactance diagram of the system which is formed for the particular state, so there are the three states, okay, subtransient, transient, and steady state of the fault condition, the current and the voltages in various part of the system can be determined by using following some of the methods, that is Kirchhoff laws, Thevenin's theorem, and by forming the bus impedance matrix. So let's see, just I will brief about this Kirchhoff law. So we need to appropriately select the base values and to determine the pre-fault condition with help of the reactance diagram of the power system. Okay, so then we have to calculate the internal EMF of the synchronous machine and the pre-fault voltage at the fault point using the pre-fault current. So draw the fault condition with help of the reactance diagram. So this is the same as the pre-fault reactance diagram, except that the fault is represented by a short circuit or by specified fault impedance. Then we need to calculate the per unit values of the fault current in various part of the system, okay, and the fault point. Then we have to calculate the actual value of the fault current or obtained by multiplying the per unit values. So actually these are the three things, but some of the numericals they will do by Kirchhoff law and the Thevenin's theorem. Okay, I will explain this the Thevenin's theorem. Okay, so for me it is Thevenin's theorem is somewhat handy, and it is very easy than with going for the Kirchhoff law. So preferring means I am preferring the Thevenin's theorem than the Kirchhoff law. So let's see the Thevenin's theorem. Okay, this is the Thevenin's theorem. So we know that as the name implies, the Thevenin theorem, which is employed in the case in this case. So these are the some of the following procedure which are followed to calculate the voltage and the current under symmetrical fault in this approach. So first we have to select the appropriate base value. Okay, this is important. So there are the different type, that is generator and the transmission line. So if they are mentioned, then we have to go with what they have mentioned. If not, okay, then we have to see whether the generator is feasible or the transmission line is feasible. Okay, and determine the pre-fault condition reactance diagram of the given power system. Okay, then this is important. We have to calculate the pre-fault Thevenin voltage at the fault point using pre-fault current. Okay, so this is important. If the system is unloaded, okay, sometimes they will mention that this is one of the example. So it is working at 60, but it is tapped by 66. Sometimes that's the case. Okay, 60 by 66 we are supposed to take. If they're not mentioned, then we have to take that pre-fault voltage will be of 1 per unit. And then we have to determine the Thevenin's impedance of the system at fault by short circuiting the voltage source. This is important to calculate the impedance. Okay. Then we have to draw the Thevenin equivalent at the fault point. Then the per unit value of the current which is given, because already we will be calculating that the voltage, okay, V Thevenins and Z Thevenins, and plus ZF value. Okay, so resulting you will get the current. So this is multiplying the per unit value by the base value, which will gives an actual value. Already we know that. Okay, hence so ZF is nothing but the fault impedance of the system. So whereas in case of solid three phase, if it is short circuited, then we have to consider ZF will be is equal to 0. Okay, then coming to the last point, that is the fault current in other part of the network are determined with the knowledge of change in the current due to the fault and the pre-fault condition. So we have to be careful while selecting this. The fault current in any part of the system which is given by sum of the pre-fault current, which is change in the current due to the fault. Okay, so the change in the current due to the fault can be estimated by connecting the Thevenin source with reversed polarity at the fault. Okay, so this is one thing, and replace all other sources by zero value sources. Now the current in various part of the system are changed in current due to the fault. So these currents are calculated using any convention technique with help of so KVL and the KCL also sometimes you will use it. Okay, this is what is a Thevenin's theorem. So by looking at this, it's look that somewhat complicated. Okay, so let's see if we will understand that solving by solving some of the numerical, we will understand the concept. So how and where we need to apply all these things. But before proceeding with this, we need to refresh once again what are all the concepts what we discussed in the module 2. So without understanding that, if you're going ahead for these numericals, it is going to be somewhat complicated.